Hello, my name is Fabiola Ruiz Sandoval from Simvestav, Querétaro, Mexico. This video accompanies the poster entitled Electrocatalysts based on rhodium clusters with carbonyl and phosphine ligands for the hydrogen evolution reaction in acid medium, presented at the International Materials Research Congress 2026. Hydrogen produced by water electrolysis is considered one of the most promising energy carriers for a sustainable future. However, improving the efficiency and long-term stability of electrocatalysts while reducing the dependence on platinum remains a major challenge. Rhodium carbonyl clusters offer an attractive alternative because their catalytic properties can be tuned through ligand modification. 5 rhodium clusters were synthesized using hexarhodium hexadecacarbonyl as the precursor, and 5 different phosphine ligands: triphenylphosphine, dimethylphenylphosphonate, bis-diphenylphosphinomethane, abbreviated as DPPM, 1,2-bis-diphenylphosphinobenzene, abbreviated as DPPBZ, and 1,1'-bis-diphenylphosphinoferricene, abbreviated as DPPF. The reactions were carried out in orthodichlorobenzene under reflux conditions, producing the 5 catalysts evaluated in this work. The FTIR spectra confirm the successful synthesis of the rhodium carbonyl phosphine clusters. The characteristic carbonyl stretching bands and the signals associated with oxidized phosphine ligands indicate that both types of ligands remain coordinated within the molecular structures. X-ray diffraction patterns showed no peaks corresponding to crystalline metallic rhodium. This indicates that the synthesized materials remain as molecular rhodium clusters rather than forming metallic nanoparticles. The molecular structures were further investigated using proton, carbon-13, and phosphorus-31 NMR spectroscopy, together with ESI and MALDI mass spectrometry. These complementary techniques provided strong evidence for the composition of each synthesized rhodium cluster. Based on all the structural characterization results, molecular compositions were proposed for the 5 catalysts. Although the phosphine ligands differ, all materials preserve the rhodium carbonyl cluster framework while exhibiting distinct coordination environments that are expected to influence their catalytic behavior. SEM images revealed heterogeneous morphologies composed of irregular agglomerates. Differences in particle texture and aggregations suggest that the phosphine ligand also affects the morphology of the supported catalysts, which may contribute to their electrochemical performance. The electrocatalytic activity toward the hydrogen evolution reaction was evaluated in 0.5 molar sulfuric acid using a rotating disc electrode. All synthesized rhodium clusters were active for hydrogen evolution, although clear differences in catalytic performance were observed depending on the coordinated phosphine ligand. Catalyst stability was evaluated by comparing the electrochemical response before and after 3,000 potential cycles. Most catalysts maintain their activity after prolonged cycling, demonstrating good electrochemical stability under acidic operating conditions. The kinetic analysis revealed that the catalytic activity strongly depends on the ligand coordinated to the rhodium cluster. Among all materials, RHD-PPM-ODCB exhibited the best overall performance, showing an initial overpotential of 66.2 millivolts at 10 milliamperes per square centimeter, which is essentially identical to commercial platinum. Even after 3,000 cycles, it maintained excellent catalytic activity, together with favorable Tafel slopes and exchange current density. In contrast, the DPPBZ, and especially the DPPF derivatives, exhibited higher overpotentials, highlighting the important role of ligand design in determining the electrocatalytic behavior. These results demonstrate that tailoring the coordination environment of rhodium clusters is an effective strategy to enhance HER performance. Their high activity and good electrochemical stability make these materials promising candidates as cathode electrocatalysts for proton exchange membrane water electrolyzers, while contributing to reduce the dependence on platinum-based catalysts. Finally, I would like to acknowledge Sasiti, Litra, Sinvestav, our collaborators, and everyone who contributed to this research. Thank you very much for your attention.